Hi, this is Alex from devstories.eu. Mastering DeepChem, Episode 9 of 15. You cannot just feed a molecule into a standard neural network designed for images. Molecules are not rigid grids of pixels, they are complex webs of atoms of varying sizes and connections. If you force them into a standard grid, you destroy the structural chemistry that makes them unique. To solve this, we use specialized molecular graph models. These models are designed specifically to natively ingest the featurized graphs generated in your earlier pre-processing steps. Listeners sometimes confuse these with traditional convolutional neural networks. A standard CNN slides a fixed-size filter over a two-dimensional grid, but a molecule does not have a top-left corner or a fixed resolution. Instead, specialized graph models operate dynamically on chemical bonds as edges and atoms as nodes. They do not care about grid coordinates, they care entirely about connectivity. DeepChem provides a few specific architectures for this. The first is the GCNModel, which stands for Graph Convolutional Network. Think of a GCN as a way to gather local atomic neighborhoods. For every atom in your featurized molecule, the GCN looks at its immediate neighbors. It takes the features of those neighboring atoms, like their element type or hybridization state, and pools them together to update the original atom's features. It repeats this process over a few layers. By the end, each atom has a mathematical representation that includes context from its surrounding chemical environment. The model then aggregates all these atom representations into a single mathematical vector to predict a general chemical property, like toxicity or solubility. That covers GCNs, which mostly focus on aggregating node data. But what about the bonds themselves? A double bond behaves very differently from a single bond, and sometimes you need the network to weigh that difference heavily. This is where the MPNNModel, or Message Passing Neural Network, comes in. Message Passing Neural Networks do not just look at a molecule, they mathematically simulate how information flows between atomic neighbors. Let's say you're training an MPNN model to predict the quantum mechanical properties of a molecule. To do this accurately, the exact nature of the bonds matters immensely. In an MPNN, both the atoms and the bonds hold explicit feature data. During the training step, the model performs a message passing phase. Every atom generates a message based on its current state and sends it to its neighbors along the connecting bonds. Crucially, the bond itself modifies that message. A message traveling over a rigid aromatic bond will calculate differently from one traveling over a flexible single bond. When an atom receives messages from all its neighbors, it uses a small internal neural network to update its own state. It essentially calculates that it is a carbon atom currently being influenced by an oxygen atom on a double bond and a hydrogen atom on a single bond. This process iterates several times. Information ripples outward, step by step, across the entire bond network. After a set number of steps, the model gathers the final states of all atoms to make its prediction. Because the MPNN natively respects the true chemical structure, it excels at predicting complex quantum behaviors that simpler models miss. Here's the key insight. You don't need to invent ways to map molecules into flat arrays. By using GCN and MPNN models, you preserve the exact atomic topology of your data, allowing the network to learn directly from the chemistry itself. That's all for this one. Thanks for listening and keep building.